Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step one aside as we jump into section 10.6 in the Big Ideas Math Integrated Math 2 textbook, segment relationships in circles. We just did angle relationships in circles, and a lot of things we did lately had to do with degree measures. This is not degree measures this time. This is lengths, actual lengths of these segments within. Inside the circle, kind of outside and around the circle. You'll see what I mean when we do the theorems. A couple more formulas. Hopefully I can say enough to make sense of what they are, or at least when you practice them, you're like, all right, I've got them. And I'm sure we'll have to prove them if they don't prove them as well. There's one more section after this in 10.7. It's a little less related. It has to do with graphs in circles. So this is probably the last one that's mostly connected to what you saw before with like all these lines going through there. 10.7, I don't think we'll have to do with that because it's the graph stuff. I haven't seen the problem set, but I'm just going to say that. So this is the last one that's really connected with this stuff here. So if you want to find out more, just check out the description section down below right here. You can find the PDF of this thing if you'd like to download it. You can also find timestamps to certain things as I begin the lecture portion. We'll then do the problem set after, which only goes to number like 26 or 28 or something like that. So I'm hoping for a short video. I'm sure you're hoping for a short video. Let's go ahead and get started and talk about what they want us to talk about. What you will learn, we'll learn to use segments of chords, tangents, and secants. And they mean this in the way of finding lengths. We have some chord vocabulary here. Nothing that's like new, tangent segment, secant segment. We've talked about tangent, secant lines. Okay, segments of a chord. We've used these, just not with lengths so much. Tangent, a little bit. The others, External segment, that's not really a phrase I use itself, but I'm sure when we read it, we'll make sense of how it's actually used. I know where it's used, but I don't really say that phrase very often. All right, using segments of chords, tangents, and secants. When two chords intersect in the interior of the circle, each chord is divided into two segments that are called segments of the chord. So here, this chord CD is divided into this DE and CE of certain lengths. This AB is divided into AE and EB of certain lengths. And there's a relationship among all four of these. Here it is. If two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. It's kind of interesting. They're saying EA times EB. They're saying this times this equals this times this for any circle of any two chords that intersect. And that's really cool. And hopefully they have extreme examples of some. And it's kind of interesting when you look at them and go, wait, really? Then that means you're telling me that in this chord, in this circle right here, that I have this big guy right here and this little guy right here, that this times this equals that times that? Yes, that's what that means. Mr. Robinson, how's that possible? This thing's so huge because this thing's so small, right? What if you do 10 times 1/10? Well, that's 1. And what's 1 times 1? It's still 1. The point is you can have things, that thing offsets it so much that the product of these two equals that whole. So yes, it is, and it can be proved. Either they'll prove it or we'll prove it. So that's the formula. We'll go and use that. Now, they use algebra stuff, so we look at this example automatically right off the bat, and it looks like we get to deal with things that turn into quadratics and then dive away from quadratics. Find ML and JK. Find this length and this length, which basically means solve for x first to do substitution in the segment addition postulate. So we get to say this times this equals this times this. We get to say x times x plus 4 equals x plus 1 times x plus 2. This is straight distribution there, and this is foiling, first outside, inside, last. I'm not going to spend too long on that. It's the algebra we should know from probably your previous semester of work. And you're left with this set. X squareds cancel out. You're left with a linear thing you can solve for x. You get x equals 2. When we substitute 2 for x into here, we get 2 plus 6, which is going to be 8 for the length of JK. And we have 3 plus 4, which is the length of 7 there. And it's not that these should equal to each other, but their products will equal each other. We can even double check that part. 3 times 4, 12, equals 2 times 6, 12. So the product of those two little bits equal each other. They have some other ones. These are pretty, I'm not going to solve them, but this is x times 3 equals 4 times 6. This is 2 times x plus 1 equals 4 times 3. Those are your setups. And we'll be doing more of those. They go pretty quick. They jump into this next set. I feel like I'm in the way, but they jump into this next set here, and this is where they use the phrase external segment. It's this blue guy right here. You're going to hear me say, okay, I'm going to read what they say, and then you're going to hear me say something a little bit different when it comes to formulas. The formula thing I use will be the same each time. You'll see what I mean. A tangent segment, they don't really have a formula here. A tangent segment is a segment that is tangent to a circle at an endpoint. Now, we've used this before. Remember when we said two tangent segments are congruent to each other? This congruent to that. So we've kind of done that before, but okay. A secant segment is a segment that contains a chord of a circle right here and has exactly one endpoint outside the circle. Remember, a secant line or a secant needs to touch the circle twice, whereas a tangent touches the circle once. If you extended it forever, it only touches it twice. This only touches it once. But we want to talk about segments now because we're going to use actual lengths of them. So secant segment versus tangent. And then the part of a secant segment that is outside the circle is called an external segment. Now, they use that phrasing because this part will be important for formulas that we use. Whenever you hear me say for external segment, instead, guys, I'm just going to say outside. You're going to hear me say outside, and even this I'll call outside. You'll see what I mean when we talk about it. There's outside, there's inside, there's whole. There's outside, and there's whole. So, anyway, they have phrases, but I'm going to read off there so we know them. Segments of secant's theorem. Let's use a formula and see what this formula is all about. If two secant segments share the same endpoint, E, outside a circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. They show EA times EB equals EC times ED. Once again, this can be proved. It looks like they're going to make us prove them. They're very quick proofs, actually, with similar triangles. The way that I'm going to say these, guys, because I'm going to go to all of them again, notice that this is the outside. EA is the outside. EB is the whole segment. Outside times whole. EC is the outside. Whoopsie, I was going to write whole. EC is the outside. ED is the whole. We're doing outside times whole equals outside times whole. Okay? Outside times whole equals outside times whole. We're going to do that for kind of all of these. Just like, remember, if you saw the last section on, I talked about things with inscribed angles, you're always doing half the measure of intercepted arc segment things. We're doing that here. So find the value of x. We're going to do here, outside times whole equals outside times whole. 9 times, not 11, 9 plus 11. 9 times 11 plus 9, which is 20. Whole thing is 20. Whole thing is 20. This equals outside 10 times whole is x plus 10. Right? So outside times whole, 9 times 20 is 180. 10 times x plus 10, you distribute that. You can subtract 100 and divide both sides by 10. You get x equals 8. They just said solve for x, and there's that one. This one, again, would be outside times whole equals outside times whole. This is 6 times 15 equals 5 times x plus 5. Outside times whole equals outside times whole. I'm not going to do kind of the rest there, but that's the idea. All right, segments of secants and tangents theorem. They're going to say all these words. I'm going to read them. If a secant segment and a tangent segment share an endpoint outside a circle, right here, then the product of the lengths of the secant segment and its external segments equals the square of the length of the tangent segment. See, that's a lot to say to kind of make sense of, but they're saying if you square this guy, it's equal to this times this. So here's the way I say it. It's going to sound very familiar. Outside times whole equals outside times whole. The cool thing about this is the outside and the whole are the same thing. Doesn't change what we do. Outside times whole equals outside times whole. So that's how I'm going to use it. If you just hear me say it each time, outside times whole. That's how I'm going to do it in the problem set. So here's an example. Outside times whole, 16 times 16, 16 squared, equals outside x times whole, x plus 8. They distribute. This one's actually quadratic this time. They get x squared plus 8x minus 256. They solve using the quadratic formula. They should have a plus or minus if you remember. Those seem to be out. I would have probably used completing the square if it wasn't factorable. So their ultimate set that they get is -4 plus or minus 4 root 17. Look, I'm not here to reteach quadratic formula and completing the square. I will do them if necessary. I'm not going to reteach them. Those were from previous chapters, but that was the quadratic formula on that one. They're showing stuff. This looks like a version of one of the proofs. I'm going to do that later, I'm sure. But they're showing you another way to do it so you can set up proportions if you need to. I'm going to save the other way for that example since we already have a version of it. If we have to prove it later, we will. Find the radius of a circle. So it uses this concept here. We got this tangent. Find the radius of the aquarium tank. So they have a tangent to this point C and this distance here, 8 that they know. The whole thing would be 8 plus these 2 r's. So outside times whole, 20 times 20, equals outside 8 times whole, 8 plus r, 2r plus 8. So 8 times 2r plus 8. They distribute, they subtract, and they divide by 16. They get the radius is 21 feet on that thing. So it's kind of just a word problem with context. These setups here, outside times whole is x squared equals 1 times 4. Outside times whole, 7 times 7, 49 equals 5 times x plus 5. And then 12 times 12 equals x times x plus 10. Outside times whole equals outside times whole. Okay, cool. So that's the problem set, right? It looks like these will be pretty quick examples as an overall. I hope, I assume, all that kind of stuff. But let's start with the vocabulary and core concept check, and we'll go from there. The part of the secant segment that is outside the circle is called outside. They call it an external segment. That's not important to me because I just call it the outside. The whole thing is called the whole, not a secant segment. Explain the difference between a tangent segment and a secant segment. Tangent segment touches the circle once, secant segment touches the circle twice. There's probably more that we can say, but that's the tangent secant thing in a nutshell. Tangent segment touches the circle only once, whereas a secant segment touches the circle twice. All right. Okay, guys. Now, I'm not going to use that phrasing so much unless they force me to use it in problem sets. Otherwise, I'm going to do my own thing. But let's go ahead and do our own thing. Let's do numbers 3 to 26. If you listen to the lecture portion, these should go relatively quickly. I want to do some drill and kill if possible. So let's go ahead and get started here. We are going to start with numbers 3 through 6, where we find the value of x. These are chords that intersect inside the circle, so they have some broken up parts here. So on this one here, and all of them will be the same thing, we get to do this times this equals this times this. So let me start with the 12 times x. 12 times x equals 10 times 6. No outside times whole stuff, it's just that. 12x equals 60. Divide both sides by 12, you get x equals 5. They just ask for the value of x, and it's there. Yes, this can go pretty fast if there's no big quadratic stuff in the way. Number 4, once again, we got this times this equals this times this. Pretty straightforward. So we got 9 times x minus 3 equals 10 times 18. Now, there are some things that you can do. Like if I wanted to, I could divide both sides by 9 like that. That could turn that into 2 and whatever. I don't think most people will see that. So unless the numbers get outlandishly large, I'm probably not going to do that. I'll just go ahead and distribute this stuff. Like I could have divided these by 6. Anyway, 9x minus 27 equals, this is 180. We add 27 to both sides. And you can see where that would have actually saved us some time there. I think that's 23. X is 23. Yeah, if you do that alternatively, let's take a look at that. 9 times x minus 3 equals 10 times 18. Because these are divisible by 9 here, just divide those by 9. And then that's 2, right? So now it becomes x minus 3 equals 20. And x equals 23. So you still get the same answer, and you can see why that could have been a little better. Faster. Number 5. This looks like a quadratic setup. We get x times x plus 8. Yeah, it's going to ask you to do some quadratics. Equals 6 times 8. So this becomes x squared plus 8x equals 48, or x squared plus 8x minus 48 equals 0. This is factorable. This factors to x plus 12 times x minus 4. And when set equal to 0, we can solve using the zero product property. X either equals negative 12 or x equals 4. Now, the problem with negative 12 is when you substitute it into here, we get negative 12 as a length here, and negative 4 is a length there. And you can't have negative lengths. So negative 12 will be an extraneous or obsolete. It doesn't work. Only x equals 4 works. And let's double check that that one works. We get 4 times 12, 48, equals 6 times 8, which is 48. That works. It's not that negative 12 times negative 4 doesn't equal 48. It's that you can't have negative lengths. Okay, and number 6. Doesn't look like a quadratic to me, at least. 2x times 12 equals 15 times the quantity x plus 3. 2x times 12 and 15x plus 45 goes there. Distribution, we get to subtract 15x from both sides and divide both sides by 9. You get x equals 5. So they didn't want full lengths. They just wanted those values of x, and all's good. All right, let's go to numbers 7 through 10, where we find the value of x. Now, I've claimed this as simply as outside times whole equals outside times whole. And I'm going to maintain that so there's no trickery about, oh, these are different than those. They're not if you use that same concept. It's really 7 through 14. That's all going to be the same to me. So on number 7, the outside of this times the whole, I'll color code these the first time through. After that, probably not. Equals the outside here times the whole. So when I'm talking outside, we're talking about that 6 times the whole thing is 6 plus 10, right? The whole thing is 16. You have to do 6 plus 10 there. Whoops, I'm going to close the parenthesis there with black. Equals the outside on this one, 8 times the whole here is going to be x plus 8. You remember, you have to add that whole set. It's not outside times inside. It's outside times whole. This is one of those things I could divide these by 8 here, but let's just multiply that out. We get 96 equals 8x plus 64. Subtract 64 over, that's 32. And divide both sides by 8, you get 4. They only ask to solve the value for x. That's the value for x. Number 8. Outside times whole equals outside times whole. This time I'll actually write the things out. Let's do x times x plus 4. That's my outside times whole equals 5 times 5 plus 7. I want to ensure that you understand it's that whole thing, not just 5 times 7 and all that. So this becomes x squared plus 4x. 5 plus 7 is 12. 5 times 12 is 60. So this becomes x squared plus 4x minus 60 equals 0. You want to set equal to 0 to solve by factoring, if you can, which you can here, or quadratic formula, but this is factorable. X plus 10 times x minus 6 will give you a product that multiplies to negative 60 and a sum that adds to 4. So x either equals negative 10 or x equals 6. Negative 10 cannot apply to this one because you plug that in, you actually get negative. And you can't have negative length, so it's going to be 6. So there's that one. That's number 8. Let's move forward to number 9. Outside times whole equals outside times whole. Part of the practice on these ones, though, does appear to be some quadratic bits. That's fine. We can get some quadratic bits. So I always like to put the variable ones in front here. Outside times, I'm going to kind of write this out. Whole, x minus 2 plus x plus 4, excuse me. Boom, boom. Equals outside times, I might as well write them both out, whole, because I got some work to do inside here. So this will be x minus 2 times, and then x plus x is 2x. Negative 2 plus 4 is 2. And this is 4 times 9. We get to distribute. This becomes 2x squared plus 2x minus 4x is minus 2x. And then negative 2 times that is minus 4. And this is 36. Hoping this is factorable, I'm going to subtract the 36 over first, and then I'm going to divide everything by 2. So we get x squared minus x minus 20 equals 0. That is very factorable. This factors into x minus 5 times x plus 4. So x either equals 5 or negative 4. Negative 4 will not work here. We would get lengths of negative 6 and 0, and we can't have those, so negative 4 does not apply. So x equals 5 will be the only answer here. The lecture portions didn't really seem to dive into this many quadratics. The one that it did was quadratic formula, so interesting that they throw a lot into there. Number 10, so they're not super quick problems with quadratics. Number 10, we have outside times whole equals outside times whole. This time they actually give you the wholes there. Outside times whole. 45 is the whole. It's now x plus 45. And here we get outside times whole. 27 times 50. Now, before I don't know if I want to do 27 times 50. I think I have ways of reducing this that I'd like to work through. Like, the 45 and the 27 can divide by 9, for example. Those can work a little bit. I'm going to shrink this a little bit. I get 5x equals 3 times 50. That's pretty good. Heck, I can divide these by 5 now instead of multiplying that. I know it's not necessarily faster, but it does work. I get x equals 3 times 10. So x equals 30. See, there are other ways you can work that out to shrink it if you don't have a calculator, you don't want to work out big numbers. I don't have a calculator in front of me. I didn't want to do 27 times 50. Now I do. 1,350. But then I have to divide that by 45, and it's just, it must be 30. All right. Number 11 through 14. Find the value of x. This doesn't stop what I was doing before. I'm still going to do outside times whole equals outside times whole. I know they treat them differently, but I'm going to color code these. Outside is blue, and the whole is green. They're both the same. So outside times whole is x times x. Something times itself is something squared, right? That's what we'll get into. Equals. And then here we have the outside times whole. It doesn't change what we do here when I just say outside times whole. They talk about external segments and secants and tangents and stuff. And those are just words. I'm going to say, the book doesn't. Who cares? 9 plus 7 is there. Okay, there's my outside times whole equals outside times whole. We get to work faster on other ones. So x squared equals 9 times 16. You know, I can take the square roots now, right? If I do square root here, you can do square root of 9 times square root of 16. That's 3 times 4. Technically, I should be doing plus or minus, but remember, the -1 will go away for this particular answer. So I think for this sake, I'll just go ahead and leave it as just the 12 for that square root thing. If a negative can be used, and I can't see a single one where it can, then I'll have to consider the plus or minus. Like I said, I can't see a single one where it can be used. Number 12, we'll once again do outside times whole equals outside times whole. Let's look at the 12 times 12 plus x. That's an outside times whole there. And 24 times itself, outside times whole. So that's 24 squared. So you can set it up that way still, but I'm still going to call it like I just did. I could divide by 12s and stuff, but I don't want you to mess up what we have there. So let's do 144 plus 12x. I like to be inventive for problems when I can, though. Equals 576, but not at the expense of you not knowing what I'm doing. 12x equals 432, I think. It's the only problem is I don't know what this is when dividing it. 360 is 30, 72 is 6, 36. My phone just went off. Let's see if it's important. Not important enough. All right, x equals 36. I'm going to venture the guess. I do believe that's what it would be. Number 13. We got outside times whole equals outside times whole. We have x times x plus 12. There's my outside times whole on top. On bottom, x plus 4 times itself. That's the outside and the whole. So we have to square that. So we have to distribute this. We're going to get x squared plus 12x equals. Now this expanded is x squared plus 8x plus 16. We have to remember how those expansions work. A squared plus 2ab plus b squared. The x squareds will subtract and cancel out. I can subtract 8x over to both sides and get 4x equals 16. Divide both sides by 4. I get x equals 4. And the last one, number 14, not the last problem in the set, but the last one in this part. Number 14, we get outside times whole equals outside times whole, or something times itself. Root 3 squared is 3. So we get x squared plus 2x equals 3. And if I subtract the 3 over, I do get something that looks factorable again to x plus 3 times x minus 1. Once again, the negative value cannot and will not apply here. So negative 3 is out, but the 1 does seem like it does apply here. So x equals 1, you betcha. All right, there's number 14. So a lot of drill and kill there. Looks like we're ending on that for when it comes to drill and kill, and we got to slow down a little bit, but we're going at good speed. Number 15, describe and correct the error in finding CD. Simple. Did they do outside times whole equals outside times whole? Oh, there's no length for this. Oh, I don't know because they don't have a length. Oh, in finding CD. I see. Let's just call it an X. Okay, let's see what they did. CD, ooh, they did inside times outside. Equals inside. No, it's not outside times inside. It's outside times whole. If I say it my way, Mr. Robinson, they did outside times inside instead of outside times whole, Mr. Robinson. The better way of saying it is they multiplied the segments. See, you would do this when they're inside the circle. I know we haven't proved that thing yet, but when the chords intersect inside, it's this times this equals that times that. They kind of treated it like that. That's not what you do. They multiplied the segments of each secant segment, internal and external, instead of the external segment with the entire secant. So that's the better wordage. Now let's solve it. Let's do this together. We got to do outside times whole equals outside times whole. So I'm going to use that bottom part that has x first. 4 times 4 plus x. See, they only did 4 times x. What I'm calling CD. X is the CD. Equals outside times whole. 3 plus 5. So 8. So this will be 16 plus 4x equals 24. 4x equals 8. When you subtract 16 divided by 4, you get x equals 2. They got x equals, or CD equals 3.75. It should be 2. All right, that is number 15. Let's go on to number 16. Modeling with mathematics. The Cassini spacecraft is on a mission in orbit around Saturn until September 2017. This must be an outdated book, or I don't know. I'll tell you what, I sure hope they don't update these books anytime soon. I've recorded hundreds of hours of video for this book, and I plan on doing it for the IM3 and IM1 books someday. We'll see when. What did I say? Cassini, da-da-da. Where is it? There it is. Is it point D? 3 of Saturn's moons, Tethys, Calypso, and Telesto, I don't know if I pronounced them right. Calypso, I did. Have nearly singular orbits of radius 295,000 kilometers. So that's not drawn, I suppose. The diagram shows the positions of the moons and the spacecraft on one of Cassini's missions. Find the distance dB from Cassini to Tethys when AD is tangent to the circular orbit. Honestly, for the most part here, I just got to go by the numbers that they have. So they wanted to find the distance from Cassini to Tethys. So this here is unknown that we're trying to find. I could call it X. Actually, I probably should call it X. Let's just call it X. Let's call this X and solve, because now X is the whole. And we don't have to deal with anything else with that. Now, they gave us the drawing. For the most part, we can run off that drawing and do the rest of it. We're going to do, and these are big numbers. That's the only problem. But we can do outside 83,000 kilometers times the whole, which is X. I don't really need parentheses for that. But outside times whole equals, and outside times whole. This is 203,000 times 203,000. So 203,000 squared. Honestly, I'm just going to divide this stuff. I'll find a calculator. I have my phone. So this squared divided by that. And I think that gets me what I need. Find the distance dB when AD is tangent. So let me get my phone out. It's a broken phone. I have this. Oh, you can't see it anymore. It's flickering. 203,000 squared divided by 83,000. Not a clean number. It's not a perfect number. So it's about 496,493.9759. I'll just put 0.976 kilometers. Hey, each little bit of kilometer would matter for that thing. So that should be the answer as far as I'm concerned. If you want to round up, we can say 494, because that 0.976 is pretty. 496,494 kilometers, if you like that one more. Did they say round to the nearest something? Where is it? No? Okay. All right, that's number 16. So it's words, but they give you the drawing. It's outside times whole equals outside times whole. No change. Number 17, another word problem with another drawing. The circular stone mound in Ireland called Newgrange has a diameter of 250 feet. They have that labeled. A passage, 62 feet long, right there, leads toward the center of the mound. Find the perpendicular distance x from the end of the passage to either side of the mound. So they have everything labeled. Now, this is not an outside times whole equals outside times whole thing. These things are intersecting inside the circle when it comes to chords. So we kind of have, I'm going to redraw it just so you can kind of see exactly what's going on and what numbers we might have to manipulate. So we have a diameter here. So there's a center, it means it's diameter. The whole thing's 250, but I don't really want the whole thing. They showed that this part, first of all, this is perpendicular, which means when a diameter is perpendicular to it, that does make those things congruent. I don't know if that's really going to matter, but these are both x. This is 62 right here, 62 feet. Now, the whole thing here is 250. So 250 minus 62 gives us this value. So 250 minus 62 equals 188 feet. Now, that part matters when it comes to solving for x. We are going to do this times this equals this times this. So x times x, or x squared, equals 188 times 62. That's our setup. And we'll solve for x. Doesn't matter if it was perpendicular or not, by the way. That just makes both these x's the same, though, with the diameter. X squared equals, boy, I don't know. Even the square root game wouldn't be fun for me on this one, so I'm going to actually literally do the 188 times 62. I get 11656. Is that a... Is that a 12 power? Square root... Is this 144? Square root of 11656. No, it's not 144. 107.926. 107.962. 9629, so 963. This is feet. So I'll say about 108 feet. I don't know what they want us to round to. All right. That's 17. Let's move on to 18. Another word problem? What's that? Oh, is this the mound they were talking about? Oh, it's real. Okay. It probably should have been. The moons were real on Saturn. 18. You are designing an animated logo for your website. Sparkles leave point C and move to the outer circle along the segments shown. So all the sparkles reach the outer circle at the same time. Sparkles travel from point C to point D. Where's D? There it is. At 2 centimeters per second. How fast should sparkles move from point C to point N? Explain. Let's first answer what this distance is. I'm going to call this part X. It looks like that's an arrow. So 4 centimeters points to here. So as far as our setup goes, just as X isn't the answer, but as far as X goes to solve for what we need, we're going to set up that these segments, this times this equals this times this. So I'm going to do 4 times X. 4 times X equals 6 times 8. So 4x is 48, so X is 12. X is 12 centimeters. Now, this isn't the answer. It's not the answer. What we want to do with this, it's a pretty straightforward process. I can make it more complicated, not more complicated, but less logical, more math formula based if we need to. Here's the idea. Everything from this point needs to go outward at the same amount of time, but these are different distances. So from C to D, it goes 2 centimeters per second. This won't go the same rate here. This is closer to here, so it's going to go slower. How much slower? We're not answering that one. This one's going to go a little bit faster because it has farther to go. How much faster? We'll see. This is, if you want to answer it pretty quickly, 12 centimeters is twice as far as 6 centimeters. So to go this distance here, in the time that it takes to go this distance, this has to go twice as fast. So logically speaking, instead of going 2 centimeters per second, it's going to go 4 centimeters per second. Now, if you want a version of this to kind of get this answered a little bit differently, let's go like this. Distance equals rate times time. Distance equals rate times time. We know what distance on this one it needs to travel at 6 centimeters. It needs to travel 6 centimeters at 2 centimeters per second. How much time will that take? Divide by 2, you get a time of 3 seconds. That means these other ones need to take 3 seconds. That means from C to N, it needs to take 3 seconds. So if we use the 3 seconds there, the distance it's going to travel, distance is rate times time, it'll travel 12 centimeters at what rate times 3 seconds? 3 seconds times what rate? You divide both sides by 3, you get a rate of 4. 4 centimeters per second. That is double that of the 2 centimeters per second. So there's a logical way to answer it. There's a mathematical way to answer it. Distance, rate times time. There are a bunch. You can probably set up a proportion of sorts if you wanted to. But that's our idea, number 18. All right, number 19, proving a theorem. Write a 2-column proof of the segments of chords theorem. I think that's this one. Plan for proof. I think I know what to do for the proof, but they're giving me certain letters, so I'm going to use them. Use the diagram. Oh, let me borrow that diagram. Give me one moment. Use the diagram from page 614. I don't have... Do I have pages on here? You can just look at me while I'm talking about this stuff. So this is... I'm just going to say out loud, this is all about similar triangles on these things. So they're talking about drawing these other guys here. So I got the picture. All right, we're here. The wrong page. We're here. Okay. Where's me? Here we go. Where am I? Where is me? So there's the diagram. This is the segments of chords, I think they said. Segments of chords. They said draw AC and DB. I don't know if we need to say that in our proof. Like draw this by construction or whatever. So we're going to draw these two. This is where your triangles come from. Show that triangle EAC and EDB are similar. Use the fact that corresponding side lengths and similar triangles are proportional. Yes, this is what it has to do with. So, you know, I don't think I need to write out given and prove. But ultimately, we need to prove that this times this equals this times that. That's what we're going to get to. So as far as a 2-column proof goes, I guess I don't have room up there. So let me just do this down here. We're going to do statements and reasons. Statements, reasons. Yeah, I don't know if I need to state that I need to draw those two things because they told me to draw it. I think I don't know. Well, okay, so what's given? What are we given? We're given 2 chords inside the circle and they intersect, okay? So my first given I'm going to write is that AB and CD are chords intersecting in the interior of the circle. It matters that it's in the interior versus the exterior. AB, segment AB, and segment CD are chords intersecting in interior of circle. Otherwise, I'll just say given, see drawing, which is, I guess is fair to say as well. But this is a nice proof. They're all nice, quick, and easy proofs to do. Okay, now, here's the thing we can do. We can prove any of these. We're going to prove the triangle's similar. The similarity thing we're going to use is based off angles. So we're going to use angle, angle. I could technically do angle, angle, angle. That's pretty easy as well because of how this is going to relate. I'm just going to do one set of each and make it unique. Like, for instance, these right here. These are congruent vertical angles. Congruent vertical angles. So there's one set of angles that are congruent. Let's call this angle AED and angle CEB. Because vertical angles theorem. Now, what's another set of angles we can show congruent? If you remember the last section we just did, actually this isn't the last section, it's the one before that, on inscribed angles. Notice when we drew this AD and CB, let's look at this for example. Look at this angle ADC. That is an inscribed angle, folks. It's an inscribed angle with this intercepted arc AC. Now look at this angle here, ABC. ABC is also an inscribed angle, folks, with this intercepted arc. It's the same intercepted arc. 2 inscribed angles that share the same intercepted arc are congruent to each other. I forget what the theorem's called, but those 2 angles are congruent to each other. This one here and this one here. They are inscribed angles with the same intercepted arc. I'm going to call it inscribed angles of a circle theorem. Or I can write out a statement that says inscribed angles that share the same intercepted arc are congruent. But that's angle ADC and angle ABC. Or let's say, actually, let's do them within the triangles. I'll call them their inscribed angles, ADC and ABC. So angle ADC is congruent to angle ABC. That way you're kind of calling them by their inscribed angles, even though we're doing the triangles. Inscribed angles of a circle theorem. That might be the name. So we have angle, angle, guys. We have this triangle similar to this triangle by angle, angle. I can call it ADE and CBE. This is the angle, angle similarity theorem. All right, 2 more steps. 1, corresponding sides of similar triangles are proportional, so we're going to set up a proportion here. Now, the ones that we care about, I don't care about the AD and the CB. I care about these ones, the ones that make up the chords. So I can say, what are parts that correspond? DE clearly corresponds with EB. Okay, so I can do DE over, let's see, what letters do they say? I think they go from E outward. So I'll say ED over EB. So I'll say ED over EB equals, those parts correspond, and then we need to do these other parts that correspond here, EA, and EC. ED over EB equals EA over EC. EA over EC. And I'll say corresponding sides of similar triangles are proportional. I've used that one before. I have to say it out loud to know what I'm spelling. Otherwise, I'm just used to CPCTC. Okay, so number 6, we can cross multiply. Multiply both sides by EC, and we get ED times EC. I'll show you what those look like in a second. Cross multiply these two, I get EA times EB. I feel like I want to do these alphabetically, but that's okay. ED times EC, what are those? ED times EC, those two segments right there equals EA times EB, those two. That's just multiplication, cross multiply, cross multiply. Cross multiplication, whatever you call it. So that's the verb. So that's the proof, guys. That's the final statement there, and that's the one that says that those two things of chords multiply with each other. It's by similar triangles that we do all of these ones, really. It's all angle stuff. So that is number, how long have I gone? 41 minutes? I want to beat the hour. That's number 19. We still have 7 more problems to do. Number 20, oh, we have 3 more proofs to do. I don't know if I can beat the hour. Number 20. Prove the segments of secants theorem. Hint, draw diagram, and add auxiliary lines. Okay, let me use the diagram they had before as well and do the same kind of stuff. So let me get to it. Segment. Excuse me. I drew all over this other one, so I got to kind of get rid of it. Oh, let me use the formula they have on the bottom as well. So I'm stealing a formula. I mean, I know that it's outside times whole equals outside times whole, but I'm going to put it here so we say this is what we want to prove. If it's okay, I'll make it. I probably want to get this big. Hope that it was okay that some things got cut off here before. So we're going to prove that. So this time I can state kind of like, given I have secants of these things. Did they want a 2-column proof? I guess last time we did one, so we can do one here. Considering we're going to do similar triangle stuff that we had before. We have secant segments. Now they intersect at point E outside of there, but if I just call them EB and ED, then the inference is that E was concurrent point. So statements, reasons. Step 1, I can say that segment EB and segment ED are secant segments. Obviously, they both intersect at E. Segment secants, I was going to say. That's perfect. Secant segments. So that's given. All right, this one is not necessarily trickier, but did they mention auxiliary lines? Yeah. They say, prove the segments of the, hint, draw a diagram and add auxiliary line segments to form similar triangles. You might not know where to go with this one. I've done this proof many times before. So we go from A to D like this, and we go from C to B. We want to prove that these triangles are not necessarily congruent, but similar. That this triangle EBC, this triangle here is similar to this triangle EDA, basically. And then we'll use the corresponding sides are proportional thing. So here's what we do. We'll do the same thing. We're not going to say vertical angles here because it's not these triangles we're talking about. We need to do lengths with the outside. So vertical angles are a no-go. But what we do have, like last time, are 2 inscribed angles here, like this B and this D, that share the same intercepted arc. So they're congruent. It's the same thing that we just saw from the last one. So I can call this angle ABC and angle CDA. So let me do that. Angle ABC. Angle ABC is congruent to angle CDA, I believe we called it. Yep. That is the inscribed angles. What was it called? Inside a circle theorem? Inscribed angles of a circle theorem? Let's see. What did I write before? Inscribed angles of a circle theorem. Okay. The next one. We don't use this as often, or we haven't in quite some time. Angle E. Angle E is in both triangles. It's in this triangle, boom, 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 and it's in this triangle, boom, boom, boom. It's congruent to itself. This is the reflexive property. It's a shared angle in both of these. So can I just say angle E is congruent to angle E? I'm going to. Angle E is congruent to angle E. This is the reflexive property of congruence, a shared angle. Now we have angle, right? We have a triangle here in EAD. It's similar to this triangle here in ECB. Boom. So these two triangles are similar by angle. Triangle EAD is similar to triangle E, I think I said CB. Yup, by angle. Okay, the important part for us is to make outside times whole equal outside times whole. So I need to involve EC. Well, I need to involve these ones. But I need to involve EC somehow. I need to involve ED, although those don't correspond. So EC is to EA, right? The purple in this purple triangle, that EC is that EA here. EC over EA equals, go back to the purple triangle, EB, and then back to the green triangle, ED. So EC over EA equals EB over ED. EC over EA equals EB over ED. Corresponding sides of similar triangles are proportional. And last, we're going to cross multiply. Let's make it look the same. I guess EC and ED will go on the right side, but I multiply. Notice how ED multiplies up with EC. So I'll get EC times ED. I'll just write it over here. Equals, I guess they do EA times EB. Cross multiply, yep, EA times EB. EA times EB. Sorry that it kind of went the other direction, but I wanted to look the same. Cross multiply. Okay, there's another proof on that one. I'm going to move forward. I need to see if I can break that hour mark. Number 21, proving a theorem. Use the tangent line to circle theorem to prove the segments of secants and tangents theorem for the special case when the secant segment contains the center of the circle. Oh, the tangent. Oh, segments of secants and tangent. Okay, so 21. What I'm thinking they're saying is, I thought the first part, I thought they were saying two different, I don't know. What I think they're saying is do the theorem of like the whole outside times whole equals outside times whole thing, but one of them, one of them's the tangent like that. But they said make a secant. I guess, do I extend this? I guess I keep going. Secant, right? They said the secant goes through the center. So they said prove this, but use the tangent line to circle theorem. I think that's the one that's saying that you make a right angle with the tangent right here. Wherever it intersects, I'm going to make it right angle most looking like that, that you make a tangent there. We're proving that whole outside times whole equals outside times whole thing. So if it's okay, I'm going to use variables. Outside, well, here's the thing. I can call this a radius, so I'll just call this one R. I guess I need this whole thing. These are all R's as well then, right? If those are all R's, then I have, I don't know what I'm trying to do here. I have unknowns here, and these are two different lengths. I'll call them X and Y. I need to say this outside times whole equals outside times whole. I need to prove that X times itself equals Y times Y plus 2R. Now, I don't know if it's worth me, if it's any value of me expanding this out or leaving like that, but I need to prove this. And they said use the tangent thing here. So here's my guess. We got to use Pythagorean theorem on this. I don't know what we're going to solve for, though. We're just going to write out, maybe just use the relationship. I'm trying to think how that would work. I'm going to do x squared plus r squared equals r plus y squared. I guess y plus r squared. So let's use Pythagorean theorem. x squared plus r squared equals, here's the hypotenuse. Remember, I'm just talking about this part. So y plus r squared. I just don't know what I want to do with this as a whole. Do I get r by itself? I guess I get x squared by itself. I probably just get x squared by itself. X squared plus r squared equals, and then this becomes y squared plus 2yr plus r squared. If I subtract r squared, yeah, I think this works out. If I subtract r squared from both sides, this goes away. And now I have x squared equals y squared plus 2yr, and I have a common factor of y. When I factor that common factor of y out, I am left with y here, and here I have 2r. So that seems to connect with this. I guess that's it. I guess it's just showing that that relationship still holds true. Did we prove this one earlier using the other thing? No, we didn't do that one. So they're using, I never would have proved it this way. Interesting. I would have proved similar triangles, but they use the tangent thing to work it out, and that works out. They relate. I just got x squared by itself because this one has x squared by itself, so I proved it, and it seems to work. Okay. Number 22. You prove the segments of secants and tangents. Oh, okay. So now we get to do the proof with the similar triangles format. So this is one I know what to do. Let me copy and paste that one over as well. Let me find it. I just don't show this right here because I have to go back. Basically, I'm going back to this page. I just need to change my numbers thing. So I'm going back to this one. I'm copying this one over. And then when I go to these other pages, it looks different in the other parts. So there we go. So now I'm going to come back to this and paste. There we go. All right, we want to prove this one using a 2-column proof, similar triangles like last time. I wonder how much I can use from the previous stuff. I don't know if I can really use anything. But number 22, prove. All right, EA squared equals this. The auxiliary line, actually lines. The lines that I want to draw for this one go like this. I'll do it in green so you can tell. From A to C and from A to D. There are actually 2 sets of similar triangles in here, and they might not be so easy for you to understand where they are. I'm going to hopefully point them out for you, and you can see them as best as possible. I don't know if color coding them will be the way or what, but let's go to our statements and reasons. We have a tangent line. EA is a tangent and ED is a secant, and draw auxiliary lines. I forget if I'm supposed to be saying draw auxiliary lines, but statements and reasons. So we're going to be proving that one there. The way that I would start it off is say EA is a tangent, ED is a secant, and then go off of that. So that kind of shows that they're both meeting at E. EA, that was EA, right? Yes, EA is a tangent and ED is a secant. Tangent segment. That's given. Okay. I feel like I need more room on the statement side, but that's okay. Sometimes the other things will be a little bit larger. Okay, you saw last time. Now, first of all, the similar triangles, remember, we got to find out that this outside times whole equals outside times whole. So we got to relate these parts, which means these parts will be involved in both your triangles, which means E is involved in both of them. Now, E, we saw last time, was congruent to itself by the reflexive property in these 2 triangles, so I'm going to do the same thing as I did before. Angle E is congruent to itself by the reflexive property. Reflexive prop. Now, the other ones I'm going to find congruent are like so. First of all, and this might not be very obvious, but we have an intercepted arc. Let's see where I can find it. It's that angle. Let's see. So here's a tangent. This angle right here. No. Am I saying that right? Not that one. This angle right here has an intercepted arc, because notice it's this chord with this tangent line. See that in purple? This one right there, let's use a double arc, has this intercepted arc AC. Do you see another inscribed angle with the intercepted arc AC? I do right here. Sorry, I have a here. This one also, ADC, also has the intercepted arc AC. So these 2 angles, treat them kind of like inscribed angles. These 2 are congruent to each other. It's kind of weird looking. We find these, but this is congruent to that. So it's angle EAC congruent to angle ADC. Angle EAC congruent to angle DAC. Now, I don't know if I can say that straight up. I don't know if I can say inscribed angles of the chord theorem, but that's how I've been stating it to you guys. This is basically a full rotation of the inscribed, because this would be the same here, and this would be the same here, all the way till you get to the tangent. And once you get to the tangent, it still keeps it there. I might be over expressing that part, calling this an inscribed angle in reality, but I'm going to give it that notion because it's still half the measure of this intercepted arc. They share it. Or do we have to say that they're both equal to half the measure? I might have to do that. Let me do this. I'm going to write another 3. But I might have to say that the measure of angle EAC, is half the measure of arc AC. I don't know what the name of the theorem is, though. Angle tangent to a circle theorem? I don't remember what it's called. Well, this is a chord, so tangent and intersected chord theorem. I don't remember. I remember they have weird names. Tangent and intersected chord theorem, not short theorem. So now the other is going to have the same thing, right? Step 4. I really got to lower this 3. I think it's going to be a few steps if I do this now. Step 4 will be the measure of angle ADC is also half the measure of arc AC. So measure of angle DAC is half measure of arc AC. That's just an inscribed angle theorem. Inscribed angle measure. Measure of an inscribed angle. Measure of inscribed angle theorem. Now, the idea is they both equal the measure of arc AC. Therefore, they equal to each other by the transitive property of equality. So, measure of angle EAC equals measure of angle DAC. And I don't know if I needed to include all this, but the other one, they don't call it inscribed angle. I treat it exactly like one. It really is. Transitive property of equality. And then finally, by definition of congruence, statement 6, these two are congruent by definition of congruence. That if these two are equal to each other, the measures are equal, then the angles are congruent. So I do have 2 sets of congruent angles in 2 different triangles. So take a look at where these triangles are. I have a triangle right here in, what color do I use? In orange, EAC. And I know it's smaller, but that's the idea of similarity, right? I have that one, and then I have one in, I'll just use green, in green right here. These 2 triangles are similar to each other. Now I hid the orange almost completely, but the orange and green are similar. And if you can find the parts that correspond, y'all, it is based on where you see the angles that are currently congruent to each other. So you can kind of use an angle. I mean, you can use an angle thing. So I'll call it triangle EAC, notice I went to single arc to double arc, is similar to triangle EDA. Triangle EAC, maybe you like the Pythagorean theorem more that we did. EAC is similar to triangle EDA. This is by angle similarity theorem. 2 more steps because we get to write out a proportion for the parts that are involved. Notice what's involved here. All these parts. AC is basically the one that's not involved. I have ED in green. Oh, AD is also not involved. ED in green, EC in orange, EA in green, and EA in orange, right? It's both of them. The difference is they don't correspond in both these parts. EA in orange is, well, it goes from the single to the double arc mark, right? Single to double in the orange triangle. Notice right there. What's single to double in the green? E to D. So EA over ED equals, now let's look at the other ones. I did orange to green, right? Let's do orange EC from single to unmarked to green single to unmarked. Remember, this is unmarked in green. Don't look at the double. That's for the orange triangle. The green triangle is unmarked there. So that's EA. So EC over EA. EC over EA. This is corresponding sides of similar triangles are proportional. If you cross multiply, you get EA times EA, or EA squared equals EC times ED. And that is cross multiply. And I believe that's how, whoa. I wrote cross multiply. I believe that's how, yeah, that's how they wrote that there. So that's the final step. So yes, we were able to prove that one. Hopefully all the proofs kind of took care of themselves, guys. It's all about similar triangles. It's okay if you don't like know that. That's why I say outside times whole equals outside times whole. There it is. All right, we're not going to finish within the hour. That's okay, but hopefully we got finished with the proofs. I got 4 more questions, and I don't think any of these are proofs. Let's see how thought-provoking they can be. Number 23 on writing equations. In the diagram of the water well, AB, I guess this part's point B, AD, I guess that part's point D, and DE are known. Write an equation for BC using these 3 measurements. Where's BC? Okay, so BC is, wow. So BC is this whole thing right here. That is a, okay, so here's a diameter, which means this is an inscribed angle of 90 degrees. So measure of angle F is 90 degrees. AB, AD, and DE are known. Is there anything else that's intersecting? Is there anything in this current section outside of the 90-degree thing that I should know about? I don't know. All I do know is that AF squared, I'm looking at the legs. AF, FG plus FG squared equals AG squared. That's Pythagorean theorem. Let's break them up into parts. They're saying things that are known. So AF is broken up into AD plus DE plus EF. I don't know if I'm doing this right. AB is known, AD is known, and DE is known. So that's known and that's known. Wait. Oh, never mind. You know what? Well, sort of. CG is going to be the same length as AB because, well, I don't know. They didn't say these are concentric circles. Can we assume these are concentric circles? In the diagram of the water well, AB, AD, and DE are known. Write something for BC. BC is also an inner... Oh, time out. This does... Okay, you know what I can do? Time out. Okay, maybe I can do something here. I'm gonna leave that for a second. I can look more like outside times whole equals outside times whole right here. I'm looking at the AB, AC. I'm gonna ignore the F and the G. I do have outside times whole equals outside times whole. I can just do that for now. Let me look at that because that's a circle within, right? So let's try this. Outside times whole equals outside times whole. But they never mentioned AE really. They mentioned DE and BC, and we got to find BC. I'm going to turn AE into AD plus DE. And I'm going to turn AC into AB plus BC. All right, what do they want? So I don't think I need this thing. I'm going to use this part. At least this has more to do with this section. I don't know if F and G are going to be used. So write an equation for BC using these 3 measurements where AB is known, AD is known, and DE is known. Yes. Okay, so I'm going to solve for BC basically here. So to solve for it, it's best that I distribute. I could divide by AB first. Do I want a full fraction? Do I distribute first? I don't know what kind of answer is going to look best here. I actually don't know. I don't know if they want a full single fraction or if they'd want something with expansion on these things. I'm going to go ahead and just expand everything. AD times AD is AD squared. And then here's AD times DE. Like that. And then AB times AB is AB squared. AB times BC is AB times BC, like that. I'm basically going to subtract this AB squared over, then divide both sides by AB. So AD squared plus, I want one fraction, AD times DE minus AB squared equals AB times BC. And then divide both sides by AB, and you get BC equals AD squared plus AD times DE minus AB squared all over AB. That's an answer. There are many versions of this answer we could do. I don't know if the Pythagorean theorem thing would have worked for several reasons, and FG is never really used. There's nothing I can use that's really congruent to it in a certain way, so that kind of threw me off and doesn't really work in a way. This one at least applies to the section well. Okay, number 24. How do you see it? Which two theorems... Oh, I don't know names of theorems. I tried before. Which two theorems would you need to use to find PQ? Explain your reasoning. Well, we could use the segments of secants and tangents theorem, because that's a secant, that's a tangent, and then tangent of a circle theorem. If this is perpendicular to that, that means this is a center right here, which means this is a radius. So they didn't ask us to solve, by the way. So segments of secant and tangent, or tangent secants, theorem, and tangent of a circle theorem, I guess. Why explain my reasoning? Because those are parts that we need. I don't know, because those are the parts, yeah, those are parts that can work some things out. I don't even know what the 12 is representing. Is that 12 must be this and not the whole length, otherwise it would be more in the middle. So I assume this part's 12. If that's the case, I want to try and solve this. I'm going to call this one X. We need to find PQ. Oh, yeah, duh. Otherwise, we'd be done. So, but technically use Pythagorean theorem. Should I say that? Maybe I can just say Pythagorean theorem because we already know this is a right angle. So why don't I not call this tangent of circle theorem? I'll say Pythagorean theorem. It is a theorem after all. All right, I'll just do that because we already know that's a right angle there, so that's good. So let's find that out. We're going to do RQ times, outside times whole of that part, so x squared, x times x, equals outside times whole. 14 plus 12 is 26. So here's the thing. I'm going to compute this. 14 times 26, I don't want to mess up. 14 times 26, I get 364. I don't care what x is. I care what x squared is because I'm going to use Pythagorean theorem to find out the rest of this PQ part. Okay, I'm going to call that RQ actually now because the other one's PQ. So RQ, I should call it QR. QR. Let's get rid of that x. All right, QR squared is 364. We have to remember by Pythagorean theorem that QR squared plus PQ squared equals PR squared. Okay, that's the thing we have here. QR squared is 364, so I don't have to worry about the square root. 364 plus PQ squared, and they didn't ask us to solve. This is just me doing this on my own. 26 squared. That's PR is 14 plus 12. So 26 squared there. What is 26 squared? 676. So PQ squared, I'm going to kind of go fast on this, minus, because I don't think they really asked us to solve that. 312. Ugh. 312, so PQ is square root of 312. 4 goes into it. 75, 78 times 78 does not have any other perfect square factors. I think it's 2 root 78. I think that's the cleanest it can go. So there's the length. I don't know if I got that correct, but they didn't really ask us to solve. They said, what would you need to use to find it? All right, number 25, critical thinking. In the figure, AB equals 12. Not 35, 25. In the figure, AB is 12. Let's copy paste this. Feels like there's a lot to do. Give me a second. Read the problem for me, will you? AB is 12. BC is 8. DE is 6. PD is 4. Interesting. And A is a point of tangency. Find the radius of circle P. Okay. There's nothing that says this is perpendicular, so there's nothing that says these bisect each other like this, so I can't assume for any reason that DC is 6. I could find this here. I need to find the radius, so maybe this is the way that I link it. I don't know yet. I'm looking through the problem just like you are. If I did link this would be a right angle at the very least. At least that can help me maybe in some way. I'm thinking in terms of the inside intersecting chords. How do I find CD? PD is 4. A is a point of tangency. Right? That's not equidistant to anything of a congruent chord or anything that I see. It doesn't say, once again, that it's congruent. Find the radius of circle P. I'll probably pause in a second to think on it, but I want to first work off of what was I going to say? Oh, I want to find something. I was curious whether something like this would apply. If I extended this one out here, so it's like collinear, and maybe I could do something with that length and say like, let's find this length, but then this length is different, and then I don't really know where I would go from that one. So I don't think that necessarily works anything out either. Let me think on this one. I'm going to pause it and think on it. Just give me a moment. Okay. I think I have it. I don't know if it'll work. I think it should work. So I was talking about maybe if I extend this thing out and stuff like that, that could work. But my goal, the thing I was thinking of was like, oh, how do I figure out what this thing is here? Because what I really want to do is say like, this times this equals this times that. And that'll be fine, because once we talk about radius, we can express this length. Like this can be like r minus 4 if that's r or something like that. I think we can do it. What we do need to do is find DC. And I can find DC, but I would need to use that secant thing before. So I can do like an outside times whole equals outside times whole. I just need to have DC be like a value. Like I can give it like an x or something like that. So let's give it like an x there. So outside times whole, I have kind of like a 12 squared equals outside 8 times whole. That's 8 plus x plus 6. 8 plus 6 is 14, so that's x plus 14. So outside times whole equals outside times whole is my first step to solve for x. So that should start us off. 144 is 8x plus 112. Subtract 112 and divide by 8, we get x equals 4. Now that's not the answer, but x is 4 here. This is nice because I think what I want to do with this is that chord thing. So let me like extend this. I want to do this in like a thin way so you can tell what I'm doing. I want to extend this out here. This is what they said, find the radius. And I don't think the right angle, the only time we use the tangent thing, I couldn't think of a way. I was thinking about how to use this Pythagorean right angle here. I don't think I can, but let's use things that we're doing now. So what we're doing now is something like this times this equals this times this kind of thing. Now the easy this times this I can talk about is 6 times 4, right? So 6 times 4, these are the segments of the chords, equals, now I have to do this times this. Keep in mind, I'm trying to find the radius. I can just call it r. So let's call this here r. That's this length here. R plus 4 is the length of this segment of this chord. So I can multiply r plus 4 with, and this one here, remember, this length would be r, but I got to take 4 away from that part, and this will be r minus 4. So I think, I haven't done this yet, I think this will be r minus 4 there. And this is where we solve for a radius. I believe that's our setup. So 6 times 4 is 24. This FOIL distributes the difference of two squares. This becomes r squared minus 16. If I add 16 to both sides, I get that, and take the square root of both sides, you get r. It's only going to be the positive one. Square root of 40 is root 4 times root 10, so I get 2 root 10. Does this have any units? No. So I think that's our final answer. R equals 2 root 10, if all went well there. I just drew a segment out that could represent the two chords. The radius was involved because it went through the center, and I think that gets me my radius from that. That's what I'm going to land on. That's what I feel good in. All right. That's, if I'm wrong, I apologize. Let's go to number 26 on thought-provoking. Circumscribe a triangle about a circle. Then use the points of tangency, inscribe a triangle in the... Then using the points of tangency, inscribe a triangle in the circle. Must it be true the two triangles are similar? Explain your reasoning. No, I don't think so. Maybe. Let's kind of start with that. Circumscribe a triangle about a circle. Any one? Okay. So let's do ooh, a little too thin. I'll keep that one a little thicker there. Okay. Let's do just a random set of 3. Just boom, tangent, boom, tangent, and this one needs to meet with that other one there later. So boom. That's pretty good. Let's go right there, tangent, and I'll shorten the other one up. So, boom. They said use the points of tangency to inscribe a circle inside the triangle. So now this one, boom, boom, and boom. They said, must these be similar? I don't think so. This angle... Let's talk about angles in intercepted arcs. This angle is half of this minus that. And this angle is just half of that. This angle is just half of that. This angle is half... I don't think so. They don't look similar. I'm just going to go ahead and say that. I don't see a reason. Maybe if they're equilateral triangles, then yeah, that would work out. But outside of that, no. Side lengths... I don't think the side lengths are in proportion with each other. Is there... Well, here's something else that we know. Side length wise. If this is X, so is this. If this is Y, so is this. If this is Z, so is this. Okay. Now, these ones inside here, is there a way that we can break that up into perpendicular parts that bisect those? I don't see anything that gives proportionality to this. I don't see sets of congruent angles. The things that are measures are half of certain distances does not apply to this way. I'm just going to say no. Side lengths aren't proportional. I'm sure there's something else I can build off of that, but I'm not quite sure what it is. Side lengths aren't proportional. I also don't believe that you have angle, anything like that. I'm just going to say that that's it. That's just a no. It doesn't look it. I tried to draw as much scale as I could, and that's it. All right, guys, that'll do it for this one. This didn't quite go the hour that I wanted it to do or whatever, but hour 20 or whatever is also fine. So it's me doing my thing. You probably don't have to do these later problems anyway. But guys, that's kind of, there's still another section in the chapter on 10.7, and by and large, maybe it's something that you still have to do, but it's not going to involve like these segment things in the same way. It's going to be equations of circles, so you're going to have to get your graph paper ready for those ones whenever I make that video. But then we'll do the reviews, we'll do the chapter test thing. I'll probably have an Are You Ready packet for my own classes and stuff that you can take a look at those. So that'll do it for this one. This is Mr. Robinson. Thank you. Take care. I will see you in the next one.